Start?
Here we go. Yes. Okay. And now, Nicolai, please take it away.
Okay. Thank you. Thank you very much to all organizers for inviting me to this honorable event. And Lou, I hope you are here. Congratulations. So, okay. So I'll be talking about some kind of new view on the old result. In 2006, with Rinat Kashayev, we constructed invariants of tangles with flat connections in the complement. Since that, there has been a lot of activity sort of in this direction, but from our construction, we always knew that it's really, I mean, basic tool is quantum groups at roots of unity, and these objects, there are several versions. The version of De Concini-Katz, on the center of this algebras, there is a Poisson structure. And somehow I never really clarified what's the meaning of this Poisson structure in terms of the knot invariants. So now in this talk, I will try to explain why it's there and what is its meaning. I apologize in advance, for possible messy presentation. Somehow, it's the first time, more or less, I'm presenting this, and so we'll see. So anyway, first, let me remind the story about tangles. So, I think here everybody knows what a tangle is. So there are, maybe I should distinguish two structures. A geometric tangle is really an embedding of a bunch of intervals and circles into a cylinder R2 cross an identity. So this is our cylinder. Across a unit interval. And on the boundary of this cylinder, we choose two lines. I mean, geometrically, they can be parallel or not. It doesn't matter. And the point is that the endpoints of the intervals should belong to these lines. So there are many reasons why one should choose these lines. But so here, these lines will define the plane of projection. So we will be presenting tangles by diagrams. And the diagrams will be planar graphs on this plane of projection. So now more precisely, geometric tangle is an embedding of intervals and circles into the cylinder such that the endpoints belong to these lines. Framed geometric tangle is a tangle with the choice of framing. I think in this audience, I don't have to explain what this is. Topological framed tangle is the regular isotopy class of a framed tangle such that the boundary of the tangle is constrained to these lines. So, so we can continuously deform the tangle in this regular isotopy class, but the endpoints should belong to L. So in other words, they can move along along the line like this, but they cannot collide. So so now diagrams of tangles is the following. Again, geometric diagram is the following. You choose a representative of your topological tangle such that it projects transversely with simple intersections on the plane of projection, and that's a geometric diagram. And then a topological diagram is a graph. It's a graph on this L cross unit interval. Sorry, this is a graph, and then topological diagram is a regular isotopy class of geometric diagram. So geometric diagram is an embedded graph in this strip, and topological diagram is the regular isotopic class of these diagrams, but double singularities remain double singularities. I don't oppose here Redemeister moves. So then diagrams form a rigid monoidal category. I think it's all well known in this audience. Frame tangles formed a rigid monoidal braided category plus the frame. So for the discussion of flat connections in the complement of a tangle, we don't need a framing. The framing will come only at the very last part. So so this one is naturally braided category. So here's the braiding. And then a well-known fact that framed Redemeister classes of diagrams form a category which is naturally equivalent to the category of tangles. And this is the list of framed Redemeister moves. Okay, so in other words, now we have a tool that has been used in this business for many years. We can think of framed tangles, which are three-dimensional objects, in terms of Redemeister equivalence classes of diagrams, which are two-dimensional objects. Okay, so now let's turn to flat connections in the complement to a tangle. So, there are several. Actually, there are two descriptions that I will mention. First is the global description, which is kind of a tangle version of Wirtinger description of representation space of the fundamental group of the complement to a knot. So the goal is now this representation space, and it can be described as follows. Just it's a Wirtinger description of this representation. Say, so we assign group elements to edges of the diagram, of a diagram of T, dt, and according to the following rule. So if we have a double crossing, the element assigned to this edge, that's element G, is the same as the element assigned to this edge, G. The element assigned to this edge, H, is not the same, but it's conjugate to the element assigned to this edge. So Wirtinger's theorem is that conjugacy, so this is the description of the representation space, and if you mod out by the diagonal action of G of the group, that describes the moduli space of representations, in other words, the character variety of the knot. So the idea of this description is very simple. So you choose a base point that is, say, significantly to the left of the diagram, and then you take the you take a path that goes around the segment of the tangle that is sitting above this edge of a diagram. So this is a segment of the tangle T above the corresponding edge of the diagram. And the Wirtinger rule follows immediately if you take the holonomy along this. So if you take this picture, you can slide the path corresponding to the group element. Clearly, the holonomy will stay the same. But if you will do similar procedure with the path corresponding to the element H, at the end of the day, you will get the conjugation with G, because you have to go back to the base point P. And so theorem, Wirtinger theorem, applied to tangles, is such decolorings of edges of the diagram are in bijection with elements of the representation variety, which is mappings from pi1, the fundamental group of the complement to a tangle with base point P to G. It also gives the description of the character variety. And remember that tangle is, it's a tangle, so there is a top boundary and the bottom boundary, and on each of these boundaries we also have the representation variety of the fundamental group, and we also have the character variety, which is this one, and we have natural projections. If you fix a representation rho of the fundamental group of the complement of the tangle, you can restrict it to holonomies that go around this upper part of the tangle, or you can restrict it to the holonomy that goes around the lower part of the tangle, and that gives two projections, pi upper and pi down, to the corresponding character varieties. So this is the structure that we have for the tangle. We have the kind of master character variety. These are conjugacy classes of representations of the fundamental group of the complement to a tangle, and we have the projections to these varieties corresponding to pi1 of the complement to endpoints in R2. Okay, so now we can add this information to the category of tangles. We will get a new category, kind of tangles G, where objects are the same as in the category of tangles. And in addition to these objects, we have a fixed isomorphism class of representations of a representation of pi1 of the complement to these endpoints on a plane to G. So we have this. So these are the objects. So rho is the representation of the fundamental group in G, and rho in brackets is the conjugacy class of this representation. And morphisms, the same. Morphism space of homes from the object epsilon comma rho and to the object sigma comma rho 2 are the following. These are all tangles which are objects in the category of tangle, but in addition to a tangle, now it's actually a pair. We also have to fix a representation, conjugacy class of the representation of the pi1 of the complement to a tangle into G, such that it restricts to rho 1 at the bottom part, and it restricts to rho 2 at the upper part. And then natural compositions and so on. So it's a category. It's just kind of, we added extra information to the category of tangles. Equivalently, this category can be described as the category of G colored diagrams, Wirtinger colored diagrams, modular Erdemeister moves. So now we remember that there is such a category, and let's describe the same category in a different way. So this is what we did with Kashaev, same picture. So we have tangles, diagrams, but now let's do the following. So this is a diagram of an unknot. So for example, we can this diagram is a projection of a real unknot. I denote it by T. So it's a projection of a real unknot. So it goes down, and we have this cylinder that is pi inverse of the diagram. And in this cylinder, we really have a unknot. So, but you see, everything is oriented. So it means that the pre-image of the diagram, of this particular diagram, creates some kind of cylinder. And the unknot separates this cylinder into the negative and positive part. So, so we have this structure. And then if you take any tangle, its diagram is a graph. So it consists of double intersections, images of the double intersection, actually double intersections, and edges between them. So we take an edge, E, and take its pre-image with respect to this projection. So we got this kind of infinite, not a cylinder, but maybe a strip. And then this strip is separated into negative and positive part by a segment of the actual tangle. So it's written here. So we have this structure. So with each tangle with fixed projection, we can associate this system of walls, which are separated into negative and positive part. Okay, so now suppose that we have a flat connection in the trivial principal G bundle over the complement to this tangle. Locally, and since the bundle is trivial, also globally, we can identify connections with one forms. I mean, we can identify them, but they transform differently because they are connections with respect to the bundle automorphisms, or as physicists call it, with respect to gauge transformations. So this gauge transformation in our case, it's just it's a group of mappings from the complement to our tangle to G. So these are the gauge transformations of connections. Then the curvature of connection A is a two-form, and two forms, they are honest. The curvature is an honest two-form, so it transforms as a form. And this is as a connection. So now we have some natural moduli spaces. So obviously, flat connections are very special. They are special because the holonomy along any path, two paths that can be continuously deformed one to the other, is the same for flat connections. So we naturally use them to describe the representation and character varieties. So moduli space of flat connections is just the following. We take all flat connections and mod out by our gauge group GT. And then this space is naturally isomorphic to the character variety. So it's I mean, from combinatorial point of view, it's a strange description because you started with an infinite dimensional space, you mod it out by the infinite dimensional group, and you ended up with something finite dimensional. But in fact, as you will see, both descriptions are useful. So we can choose a base point. We can consider a pointed gauge group, the gauge group that is trivial at some point. And then if you do the same, if you will take all flat connections modeled out by this pointed gauge group, then you will have the representation variety supported by with the base point P. So it's a space of homomorphisms from pi1 to G before taking conjugacy classes. Okay, so now assume that G is simple, fix Borel subgroup. So then there is a unique decomposition of every element of X into X plus X minus, so that so X plus X minus are elements in the Borel subgroups B plus B minus, with the condition that the Cartan parts are the same. So exponentiating B plus B minus, we get Borel subgroups, and so this is what we have. And then the important subgroup of B plus cross B minus is something that's called G star. It's the dual Poisson-Lie group of group G with the standard Poisson structure. So it's the collection of pairs of elements from B plus cross B minus, such that the Cartan part of G plus is equal to the inverse of the Cartan part of G minus. Now, G star and G are kind of in birational correspondence. So it's a birational, this mapping is a birational isomorphism, but not quite, up to the fact that it's 2 to the R to 1 covering. R is the rank of the Lie group G. So, and then the next step, let's do the following. So we have, let's choose very special representatives of gauge classes of flat connections. Let's trivialize A everywhere outside of epsilon neighborhoods of these walls, of these walls. These ones. So and in addition, we can do it in the following way. We can trivialize them everywhere outside of the epsilon neighborhood of an epsilon neighborhood of walls, and in addition, we can make A, say, on the negative wall to be in G minus, A on the positive wall to be in G plus. So then, if we denote by G plus minus, okay, so before this, because we have now these very thin walls where the flat connection is non-trivial, and it's trivial everywhere else, if we have such wall, and if we have a path through this wall, so then integrating flat connection along this path will give the holonomy, but this holonomy will be trivial everywhere here. It will gain non-triviality only when you cross the wall. So this is what I mean by G plus minus be the holonomy of A through walls W plus minus. So this is the picture. That's a path connecting 2 points in different chambers that goes below the wall, below the segment of T, and above the segment of T, through these walls W plus minus. So such special representative of gauge classes of flat connections assign pairs of elements G plus and G minus to each edge of our diagram D. So having in mind this mapping, I'll just say that we assign a group element to an edge without specifying whether it's in G or in G star, but I always assume that it's actually in G star. So now, the same as in the Wirtinger description, there are relations of group elements assigned to edges of the diagram around the double intersection. I will not go into the details then because it just will not be enough time. But here is the answer. So by the same technique, you just have to deform path, this blue path that give the holonomy, you will get these relations. So it's kind of, it's an implicit description of a mapping from the pair AB to from the pair CD to the pair AB. So you see, you know C and D, so first you compute A, and then you compute B using this formula. And the same for the negative crossing. So these are the birational relations modulo this covering map. And so we'll call these colorings local colorings or G star colorings. Local because, I mean, they are really local. There is no base point now anywhere. So then a little theorem that local colorings are compatible with Reidemeister moves birationally. And again, birationally, assuming this covering. So corollary, local colorings is not really a structure on a diagram. It's a structure on that depends on a tangle. Because Reidemeister classes of diagrams are in bijection with tangles, so Reidemeister classes of colored diagrams are in bijections with pairs, a tangle and a representation of pi1. And the representation of pi1 is from here. It's very easy to obtain. You just choose a base point somewhere. And then if you have a path, so you just take the product of elements that you gain by when you will be crossing these walls. So and then the theorem is local colorings of the diagrams modulo Reidemeister move are in birational correspondence with the representation variety for the complement of this tangle. Okay, so these locally colored diagrams, again, they form a birationally braided category, very similar to this category kind of decorated by representations of the fundamental group that I described before. So it's all the same. For the braiding, we use this rule that was mentioned before. And so up to now, there's nothing new. So this local representation, this G star coloring, this is exactly what was part of our work with Turaev from 2006. So now Poisson structures. So first of all, let me remind the local Poisson structure. So if you choose the Borel subgroup in a simple Lie group with all the words that I already said about it, so we have the subgroup of G plus cross G minus G star. It has a natural Poisson structure, which can be described in terms of the classical R matrix for the standard Lie by algebra, Lie sorry, yeah, for the standard Poisson Lie structure on G. So that goes back to works on classical integrable systems, and so this particular R matrix is, yeah, it was invented. I think it was discovered first by Drinfeld or by Belavin and Drinfeld. So it gives. So this is the description of the Poisson structure on G star. It's basically the Poisson brackets between matrix elements of group element of matrix elements of group G in finite dimensional representations. So this now is a Poisson variety. For any Poisson variety, the first question is, what are the symplectic leaves? It turns out that symplectic leaves here are the following. So you take this map G star to G, and then you take the pre-image of conjugacy classes in G. And these are symplectic leaves in G star. So, and then it turns out that this mapping that I just described over there topologically, as a mapping from G star to G star, is a birational Poisson mapping, which was discovered by Su and Weinstein in early 1990s. And it preserves symplectic leaves. It's a Poisson mapping, so it's actually a mapping. It gives a mapping from C2 to S, C2, S, C1. If you want, this is a Poisson analog of the braiding in quantum groups. So, yeah, so now we can do the following. We assume that these elements, these colorings that we assign to edges, they belong to the same conjugacy class. So so G1 is in one symplectic leaf, Gn is the other symplectic leaf, and because the braiding preserves the symplectic leaves, actually, if you have some kind of knot here, you can still assign a symplectic leaf to this knot, and so local colorings they give some subset in the representation variety of the complement to our tangle. And also it gives the restrictions to, these are the restriction maps to the upper part and lower part. And then the conjecture, so, you know, I'm giving this talk like a physicist. I'm talking about something that is not finished yet. So the claim, which is a work in progress, but it shouldn't. I mean, it's a question of doing it. It shouldn't be something complicated. The image of this mapping is a Lagrangian subvariety in the product of this symplectic varieties, and it's actually, it gives a Lagrangian, as a consequence, it gives a Lagrangian correspondence between these varieties. So, okay, so this is what we have for the G star colorings. And just a remark that, you know, we can again construct a category with G star colorings, but now the colorings will not be character varieties. The space of homes will be not the space of not character varieties, but they will be decorated by the representation varieties. Okay, so this Poisson structure, somehow it's very natural if you know about Poisson-Lie groups, but if you don't, it seems totally artificial. Why it should be there, it's not clear. So, but there is a natural Poisson structure that sort of in this part of the world, and it's the Atiyah-Bott Poisson structure. So if you consider R2 minus n points, the fundamental group is just free group generated by n elements, and representation variety is G to the n. The character variety is G to the n mod G with respect to the diagonal action of G by conjugation. So, but then Atiyah and Bott, they described symplectic structure on the moduli space of flat connections over closed oriented surface. And actually, it also gives a Poisson structure on this space. So maybe let me spend very few minutes before I'll structure my next part of the talk. How many minutes do I have? Hello?
Yes, you've got about 5 to 10 minutes.
Okay, thank you. So if we have a compact closed surface, there is a natural symplectic form on the space of connections, and then the action of the gauge group on this space of connections is Hamiltonian. So we have a moment map from the space of connections to the dual space to the Lie algebra of the gauge group. This dual space can be naturally associated with two forms on sigma with coefficients in the Lie algebra. And the moment map is exactly the map that maps connection to the curvature of this connection. And corollary of this is if you will take the preimage of 0 with respect to the moment map, mod it out by the gauge group, we will have the moduli spaces of flat connections, which is the character variety, but we will have a symplectic structure on this moduli space because it's a Hamiltonian reduction. So then similarly, if the boundary is non-trivial, then you go to Poisson variety, and symplectic leaves of these Poisson variety are the following. You have to fix conjugacy classes for each component of the boundary, and the holonomy with respect to this representation should around each component of the boundary should belong to this conjugacy class. So it's naturally a subset of the whole moduli space. And these are symplectic leaves. And if we take, if sigma, we can choose sigma to be R2 minus n points. And then we have a natural fact that our moduli space MGN is Poisson. So given a tangle, we have a representation variety, we have the top and at the bottom, and we have the character variety, MGT, and it projects to the product, fibered product of character varieties. And then here we have the subset where we fix conjugacy classes for each of the strands, and it projects to this space. It's the fibered product of a conjugacy class C, so corresponding to this path. You see, it can be slid through the tangle, and so we should take the fibered product over this. So everything is good, but so we got the natural Poisson structure on the boundary spaces. We got this projection from here to here, and the image is Lagrangian. So everything, it seems like everything that we want, but you see, before, when we were using these G star decorations, I was talking about representation varieties, and here we take the mod out, we mod out by G. So unfortunately, there is no natural Poisson structure on representation variety, which is just pi1 sigma to G. But there is a good news. Falk and Rossley in the 90s, they constructed Poisson structures on graph connections, in particular on, we can apply this construction to this graph in blue. So we have, so this is R2 minus n points. This is graph gamma. So these are the G minus G plus colorings just as before. And so as a result, we have some kind of new representation variety, from which we can, you know, if we have a path that goes around these points, we can deform it to this graph and then read out these G plus minus data, and that gives the representation of the of pi1. So this is Falk and Rossley Poisson structure in this case, and the mapping is given like this. If we have a path that go around points 1 through I, the holonomy of this path is given by this expression. So and then yeah, we have the birational isomorphism, but it should be like this. So this, it lifts Atiyah-Bott Poisson structure from this space to this space, and actually this lifting is exactly, so it's the Falk-Rossley structure. Okay, so I'm sorry, I'm running out of time before I'll come to the point. So anyway, so we have these birational correspondences, and we have two descriptions, Wirtinger description and this local description in terms of G star. Local description is good because, you know, we can say here's the de Concini-Katz integral form of quantum SL2 and specialization to a root of unity. So it has this Poisson structure on the center very naturally. The center Z0 is isomorphic to functions on B plus on SL2 star. It's a Poisson-Lie group. And then we can, so elements of SL2 star are central characters for this quantum group. And so that's just a repetition of this. And then the nice thing is that there is an automorphism of the algebra R, which is which acts non-trivial in the center. It acts as this Poisson mapping that describes the braiding of G-star colorings, but it lifts to the automorphism of the algebra, which sorry, I missed it here. But then you can apply it to the algebras sitting over certain points of SL2 star, and you get the braiding. And then you use the usual machinery of invariance of tangles and R matrices, and you get the invariance of flat connections with in the complement. And if you want to construct invariance of tangles for links, when there are some non-trivial several S1 components of a tangle, then you should use also this so-called renormalization of the invariants, because many of them will be zero. So you use the procedure that was suggested by Gear, Peteran, Miron, and Turaev. And then you have invariance of links. I'm sorry, I ran out of time. I hope it was clear what I wanted to say.